An oil cooler for a large diesel engine is to cool engine oil from 60 to 45 degrees using seawater at an inlet temperature of 20 with a temperature rise of 15. The design heat load is 140 kilowatt and the mean overall heat transfer coefficient is 70 watt per meter square per degree Celsius. Calculate the heat transfer surface area for single pass, counterflow and parallel flow arrangements. So here you are given all the temperatures, the inlet and outlet temperatures of both the fluids. You are given the design heat load and you are given the overall heat transfer coefficient. So you have to find the area, which means if you find the LMTD, you can find the area. So the idea is, let's find what is the LMTD in parallel flow configuration. In both configuration we have to find. So first let me find it in parallel flow configuration. If the flow happens in parallel, in the same direction, in parallel flow, the temperature profiles will be like this. The hot fluid is oil and the oil is changing its temperature from 60 to 45. Okay. Engine oil is decreasing temperature from 60 to 45. So engine oil is entering at 60 degrees Celsius. This is T1 and its temperature decreases to 45 degrees Celsius. This is T2. Now, let me mark the direction of the fluid. This is engine oil. This is the hot fluid. What about the cold fluid? We are using seawater as the cold fluid and the inlet temperature is 20. Because it's a parallel flow, water is entering in the same direction. So small T1 is 20 degrees Celsius with a temperature rise of 15. So it starts at 20 and the rise in temperature is 15 degrees Celsius. So the exit temperature will come to 35 degrees. Okay. 20 plus 15 is 35 degrees. This will be your T2. And the fluid given is seawater. This is our cold fluid. Now because it's a parallel flow configuration, both the fluids enter in the same direction from left to right. Now if you look at the data book, the LMTD, it is mentioned as delta T LM, logarithmic mean. If you go back to the data book, you know it's here. For parallel flow, for single pass parallel flow, it's here. Let's write the expression. T1 minus T1 minus T2 minus T2 divided by logarithm of T1 minus T1 by T2 minus T2. And you know these are nothing but the inlet temperature difference and the outlet temperature difference. Delta Ti at the inlet, the temperature difference is 40 degrees Celsius and delta To or delta T at the exit is 10 degrees Celsius. 45 minus 35, 10 degrees Celsius. So I could substitute or I could directly write it as 40 minus 10 by log of 40 by 10. And this happens to be 21.64 degrees Celsius. So in parallel flow, the delta Tm is 21.64 and we can find the heat exchange area using the fundamental equation in LMTD. Q equals UA into the LMTD, which means the area of the heat exchanger, that's what we want, is Q by U into LMTD. We know the heat transfer, Q is 140 kilowatts, 140 into 10 power 3 watt divided by the heat exchange, the overall heat transfer coefficient is given as 70 watt per meter square per degree Celsius and we found the LMTD to be 21.64. If we substitute, you calculate the area required in parallel flow. It turns out to be 92.42 meters square. So if you are using a parallel flow configuration, you will require an area of 92.42 meters square. Let's do the same thing for a counter flow. This is parallel flow. We have to repeat the same thing for a counter flow heat exchanger. I suggest you always start with the temperature profiles. We have counter flow. To avoid making mistakes in the exam, you always sketch the temperature profiles from the problem. Now engine oil is going from 60 to 45. I am assuming the hot fluid direction to be the same, left to right. So hot fluid is going from 60 to 45. The 60 degrees Celsius and 45 degrees Celsius. This is the hot fluid, oil, and the cold fluid is going from, now it's going the opposite direction. Cold fluid temperature starts at 20 and goes to 35. So 20 is here. In counter flow, the direction has to be changed, and 35 is below 45. So I mark some red. This is the cold fluid. Now the notations T1, T2 for the hot fluid, small t1 and small t2 for the cold fluid. And if you look at the temperature difference at the exit, this is 45 minus 20, 25 degrees Celsius. And at the inlet of the heat exchanger, the temperature difference is 60 minus 35 is again 25 degrees Celsius. Right? This is a special case in counterflow. When this happens, the velocity profiles are parallel. The temperature difference is the same at the inlet and the exit. So this is a special case in counterflow. If this happens, your formula will give a 0 by 0 form. You will get a 0 by 0 as the answer, and you will not be able to use the formula directly. So what is this special case? In a counterflow heat exchanger, if the temperature difference at the inlet and the temperature difference at the exit happens to be equal, that is T1 minus T2 equals T2 minus T1. If this is true, then what will happen to the LMTD? The LMTD becomes T1 minus T2 minus T2 minus T1 by logarithm of T1 minus T2 by T2 minus. Okay. What happens is, if I put the same numbers, in this case 25 minus 25 by logarithm of 25 by 25. 25 minus 25 is 0 and log 1 is 0. So this becomes a 0 by 0 form. In this case, we can prove using L'Hopital's rule that the LMTD, the logarithmic mean temperature, is either the temperature difference at the inlet or the temperature difference at the exit. So you don't need to go for formula. If this number 25 and this number equals, they are both equal, and what happens is the LMTD is same as that number. Formula will fail, and then you can figure out the LMTD is same as 25 degrees Celsius. Okay, please make note of this special case. Whenever the special case comes, you should remember that the formula you will get a 0 by 0 form for LMTD, and using L'Hopital's rule you can prove that the LMTD is same as the temperature difference at the inlet or the temperature difference at the outlet of the heat exchanger. Now we have figured out the LMTD is 25. We can go back to the same equation, Q equals UA into the LMTD, and area is Q by UA into the LMTD. Now the area becomes Similar to parallel flow, all these remains the same, only the LMTD value change. So it's 140 into 10 power 3 divided by the overall heat transfer coefficient is 70, and now the LMTD in counterflow is 25. So you see that the counterflow requires a smaller area compared to a parallel flow for the same temperatures. So this is for counterflow. A counterflow heat exchanger will require a smaller area than a parallel flow heat exchanger because its LMTD is higher. If you compare the values, for parallel flow we needed 92.42. Let me compare it. This is for counterflow. So if you compare the LMTDs, parallel flow the logarithmic mean temperature difference in parallel flow was 21.64. Whereas this is for parallel flow, for counterflow is 25 degrees Celsius. And the heat transfer areas, the area for parallel flow was 92.42 meter square, and the heat exchange area required in counterflow is 80 meter square. So you see, counterflow heat exchanger is much more compact for the same inlet and exit temperatures of hot and cold fluid compared to a parallel flow heat exchanger because its LMTD is higher. Thank you.